Hi, in this video we're going to talk about the Ionic crystalline and its application in our daily life. So here with me are Adani, Sofia, Nurin, Shazwina and Arya.
Assalamualaikum and hello everyone. My name is Sofia Alisa binti Umahide. In this video, our group will discuss the topic Ionic crystalline solids. Before we begin, here are the objectives of our presentation. First, to describe the key characteristic and nature of ionic crystalline solids. Second, to explain how cations and anions are arranged in common ionic structures such as sodium chloride, cesium chloride, and more. Third, to relate the structure of ionic crystals to their physical properties, including melting point, hardness, solubility, and conductivity. Fourth, to differentiate ionic crystalline solids from other types of solids such as metallic or covalent network solids. Lastly, to highlight real-life application of ionic crystalline materials in various industries. These objectives will guide our understanding of how ionic crystals behave and why they are important in chemistry and everyday life.
Here is the general introduction. What is solids? Solids are made of atoms, molecules, or ions that are arranged very closely together in a regular and orderly pattern, forming a complete and well-defined structure known as a crystal lattice. Because the particles are packed closely, the forces of attraction between them are very strong. Additionally, the particles do not move freely from place to place. Instead, they vibrate around the fixed positions due to thermal energy. This vibration occurs without breaking the strong bonds holding the particles in place. As a result, solids retain a definite shape and a fixed volume, since the particles cannot slide past one another or spread out like liquid or gases. There are many types of solids. We classify solids into two main groups: crystalline solids and amorphous solids. Most of the solids we study in chemistry are crystalline, so today we'll focus on them. There are four major types of crystalline solids: ionic solids, covalent network solids, molecular solids, metallic solids. We're going to spend most of our video today talking about ionic solids.
Next, I will explain the difference between crystalline solids and amorphous solids. So, in crystalline solids, the atoms are arranged in a regular and repeating three-dimensional pattern. They have a sharp melting point, more rigid, and show long-range order. Examples include potassium, nitrate, and copper. On the other hand, amorphous solids do not have a regular arrangement of atoms. They do not have a definite melting point, are less rigid, and only show short range order. Examples are cellophane and polyvinyl chloride, or PVC. Fun fact, crystalline solids are like a neatly arranged bookshelf, while amorphous solids are like a messy drawer where everything is just everywhere or somewhere. Alright, now ionic crystalline solids are made up of positive and negative ions that are held together by strong electrostatic attraction between opposite charges. In our case, the examples we are using are sodium chloride, magnesium sulfate, and ammonium nitrate. These solids are usually have high melting points, are hard and brittle, and do not conduct electricity in the solid state.
Next, let's take a look at the major properties of ionic crystalline solids. Firstly, ionic solids have high melting and boiling points. This is because electrostatic attractions between positively charged cations and negatively charged anions is very strong and a large amount of energy is needed to break the lattice. Secondly, ionic crystals are hard but brittle. They are hard due to strong ionic bonds, but when force is applied, layers of ions shift. This brings charges close to each other, causing strong repulsion and crystal breaks. Third, in this solid state, ionic compounds do not conduct electricity. The ions are locked in place and cannot move freely. However, when they are molten or dissolved in water, they can conduct electricity. This is because the ions becomes free to move and carry electrical current. Additionally, ionic crystalline solids are generally soluble in polar solvents such as water. Water molecules attract and stabilize the ions, allowing the crystal lattice to break apart. Another property is that ionic solids have high lattice energy, especially when the ions have high charges or small sizes. This contributes to their stability. Lastly, ionic crystals have regular repeating arrangement in 3D lattice, three-dimensional lattice. This ordered structure gives them distinct shapes and characteristic crystal patterns. These properties helps us understand how ionic solids behave in different conditions and why they are widely used in industry and daily life.
So now we'll be talking about NaCl, or sodium chloride, or better known as table salt, that we use in our cooking every day. It's a fun fact. One of the qualities for NaCl that can make it identify as an ionic crystalline solid is that it has both positive and negative charges. The positive cation is Na plus in this case, and the anion is Cl minus. They are arranged alternately in the crystal lattice structure, which by the way is the face center cubic, with a 6 coordinated number, meaning that it needs a 1-to-1 ratio to complete the NaCl structure, kind of. So we can apply an NaCl as an electrolyte because in its molten state, it can produce mobile ions, allowing electrical current flow. So how does it work? Sodium is more electropositive and forms Na plus when it loses an electron, and also when it's in the molten state or they're inside water, kind of like that. And chloride is more electronegative and forms Cl minus when it gains an electron. So the sodium Na plus ion flows towards the negative electrode, which is the cathode, and the Cl minus ion flows towards the positive electrode, which is the anode. So in this structure, the bottom part with the beaker, the ion flows to each other with its charges, and the wire part flows the electron, making it a complete circuit. How crazy is that? Fun fact, salt is also used to melt ice and snow. How does it work? This is because NaCl, or salt, lowers the freezing point of water, which is why it spreads on icy roads in cold countries. So now we'll be talking about the crystal defects in crystalline solids that could occur in our previously discussed examples. So first of all, we need to know what a crystal defect is. A crystal defect is an imperfection in crystalline solid caused by irregular arrangement in lattice. Currently, we only know of the crystalline solid defects and not in the amorphous solids. So as we know, there's nothing perfect in this world. Therefore, to find an ideal crystal, it's likely to not exist. We'll be talking about this topic further on in the next slide, where we talk about the types of crystal defects and what the common defect that could happen in our previous discussed examples, such as NaCl, magnesium sulfate, and ammonium nitrate.
Now I'm going to go deeper on the types of crystal defects. There are two types of it. First, we have stoichiometric defects and non-stoichiometric defects. So, for the stoichiometric defects, it occurs when there are irregularities in the arrangement of atoms, but the overall chemical composition of the crystal remains unchanged. Examples include vacancy defects, Schottky defects, interstitial defects, and Frankel defects. Now, we're going to list all the defects that happen in our discussed compounds in the previous slides. First, sodium chloride. It commonly shows Schottky defects, where equal numbers of Na plus and Cl minus ions are missing. For the ammonium nitrate, commonly shows vacancy defects and Frankel defects due to its less stable crystal structure. And the last one, which is magnesium sulfate, commonly shows vacancy defects and Schottky defects, especially during crystal formation. What else is missing? Can you guess it? Yes, it's the non-stoichiometric defects, which we haven't discussed about it yet. But okay, non-stoichiometric defects occur when the ratio of ions changes, causing the chemical composition of the crystal to change. So these defects are divided into two, which are metal excess defects, which mean extra metals, ions are present. While for metal deficiency defects, it has fewer metal ions than expected. And I wonder why. Now, these are common in transition metal compounds but are rare in what we discussed about, which is sodium fluoride, ammonium nitrate, and magnesium sulfate.
These are two important point defects found in ionic crystals. Firstly, the Schottky defect. A Schottky defect is formed when one cation and one anion are missing from their regular lattice positions in an ionic crystal. These ions leave the lattice entirely, creating vacancies because both positive and negative ions are missing in equal numbers. The electrical neutrality of the ionic compound is maintained. However, the absence of ions reduces the total mass of the crystal, while the volume remains almost the same, which causes the density of the substance to decrease. This type of defect is commonly observed in ionic compounds where the cation and anion are similar in size, allowing both ions to leave the lattice without causing major distortion. Next, the Frankel defect. A Frankel defect occurs when an ion is displaced from its normal lattice site to an interstitial site within the same crystal. This displacement usually involves a cation, as cations are generally smaller in size compared to anions, making it easier for them to fit into the voids or interstitial spaces of the crystal lattice. In this case, no ions are removed from the crystal. Instead, the ion simply changes its position. As a result, the overall density of the ionic crystal remains unchanged, since the total number of ions stays the same.
In conclusion, ionic crystalline solids are materials formed by the strong electrostatic attraction between positively and negatively charged ions, arranged in a highly ordered three-dimensional lattice. This structure makes them hard, brittle, and able to withstand high temperature. While their melting and boiling point are generally high due to the strong ionic points. In solid form, they do not conduct electricity, but when melted or dissolved in water, they allow the flow of electric current because the ions becomes mobile. Because of these properties, ionic crystalline solids are widely used in chemical industries, ceramics, electrolysis processes, and as essential components in everyday materials such as salts and electrolytes.
Here is the references that we use, and that is all from us. Thank you.